So, right at the end of last week, we did Hamming codes, right? And it showed you that it is 7 bits. You're able to correct any one single bit error, and you're also able to detect 2 errors, right? Which was quite astonishing for the time. Like, nobody actually thought that that was possible, and Hamming came up and showed that it was, and why it was, and proved that it was factually correct. Unfortunately, that's not quite enough, right? So if we're transmitting 7 bits for every 4 bits that we need to transport, that's quite a bit of overhead. But it could be useful still, or something like that. So there are some other ways that you can do Hamming code or do error correction that are much more computationally intensive. Back when Hamming did it, right, which was I believe in the 50s is when he came up with that, right? Computers were very large, and they fit in rooms, not in phones. So and those computers that fit in rooms were very slow. So having a computer a full-blown computer at every network device wasn't even feasible, right? So but as computation has things have shrank. When things shrink, they get lower power and they get faster, and you can fit more transistors in there, and so computation becomes cheaper. And it has since become economically possible to have much more complex error codes at line speed. But sometimes error detection is better than error correction. Anybody want to take a guess when error correction is better than error detection?
When you don't have a lot of bandwidth, maybe, and so you can't retransmit.
So yes, so if you are sending a space probe to Mars, right, and it takes 20-minute transit time, right, then error correction is probably much better than error detection, because error detection implies that we need to notify the sender that we need, and we'll talk about that today. We notify the sender that we need to retransmit, right? So that's one reason. What's the other? There's another reason that's not quite as intuitive. So, surprise that it might come as a surprise, but if the errors are random, so that, like, let's say you have an even distribution of errors, they can happen at any given point. So, and you have some non-trivial amount of errors, then error correction might be better. So let's take a look at why that is. So, like, let's say, gotta get last week's notes. We're gonna go for two scenarios with the same probability of error, but one is random and the other one is bursty. So let's say that you have so something that's evenly dispersed, we'll call them like random errors. And something that's not evenly dispersed, called bursty. And let's say that our probability for errors over here is the same in both instances. So I'm going to look at the right example so we don't have to go through hard math. So let's say it's 2 in 1,000. So with random errors, and let's just use frame sizes of 100, just so that the numbers are easy. Frames are usually much bigger than that. But so our frame size is 100. We have a probability error of 2 in 1,000. right? So about how many frames are going to have errors in it?
20?
So it's going to be a fraction, right?
Like 2.2.
2.
Yeah, 0.2, right? So 1/5. And over here, right, is bursties is still 1/5, right? But this is over 1/5 over the long haul, right?
So you get like a bunch of like perfect frames and then like one really crappy frame.
You'll get a bunch of perfect frames, and then you'll have a strong burst of errors. So, like, let's say you're in somebody steps on you, right, on a transmission, right? You get a long string of errors, and we'll talk ways to do that, but you get this long string, right? So here, you're having a one of every frames have a random, even dispersed error in it, right? So that means that you get 4 frames for every good one. Right, but here, let's say that it's always in large streams, and we've done some measurements, and it's always around 100 errors when it happens, right? So, which would be, if your frame size is 100 and you're getting stepped on in a transmission, then it's probably going to be about 100 errors, right? Because things being overlapped, right, and the signal is just completely destroyed. So, how many frames here are being errored? Right? If your bursts are always in 100,
Just you get 1 frame.
huh?
2. Or here.
So our probability for error is 1/5, right? But bursts always come in hundreds, right? So there's really, the most likely scenario is that one error kills 2 frames, and then in some unlikely scenario, they're perfectly aligned, right, and it kills 1 frame. So it's 1 or 2, more than likely 2, but that's 1 or 2 out of how many?
1,000.
1,000. Bad way to put that math problem. So now that we understand that, can we intuitively see why one error detection might be better than error correction and vice versa? So let's say we're using Hamming codes, right? So if we're using Hamming codes and we need to send, let's say, let's just use 100 bytes of data. How many bytes of data do we actually have to send? It's 7 for every 4, right? With the Hamming code. So if we're doing, in both of these situations, right, with a Hamming code, and you want to send 100 bytes, equals exactly how many?
175.
100, I don't know. Somebody gonna tell me that, right? 175?
7/4 times on the.
Yeah.
Yeah. I think it's 175.
So, yeah, 4 goes in there, 25, 25 times 7 is
175.
75, right? So you need to send 175 bytes, right? So our efficiency is 100 over 175. And that gives us our line rate efficiency. Now, and that is whether evenly distributed. What about here? If we're using Hamming codes, it's still 100 over 75. If we're using error detection, though, and we're going to do a retransmit, so if we're going to do a retransmit, what's our efficiency over here?
So, what's the, is it floor 2?
1 or 2.
Oh, 1.
So, and the reason it's 1 or 2 is because you have a frame, right?
Mhm.
So if the error it hits here, then this is 1, right? If it hits anywhere in here, then this is 2 because it affects both frames. But let's just go with the worst case scenario, 2. 2 in 1,000. So if we have some kind of error detection, right, we can easily accomplish error detection in 16 bytes. And we're going to go into that next. So we're going to use a 16-byte or 16-byte checksum, which is what IP and TCP use. Right? We can easily obtain that in. So that means that we have 116, right, or 100, way better rate in this circumstance. Now you can actually look, you can see that we could calculate how much data we have to do this. This is a hard-coded number, right? So 175 bytes for every single frame. And here, we got to do 116 bytes for every single frame, but 2 out of 1,000 times we're going to have to retransmit that. So it would be, our efficiency would be 100 over 116 plus 2 over 1,000 times having to retransmit it, right? So 116. Which is still much smaller number, right? So error correction can be really beneficial for you if it's going to be random, or you have a situation like, you know, talking to the Cassini probe, where error detection is just totally out of question because of transit time, right? In this circumstance where we have bursty errors, which is much like what we would see in a LAN or Wi-Fi or something else, where the transit time is very small, right? Wi-Fi has, or let's say Ethernet has, what, 323 feet for the guys that have done networking like architecture, right? So 320 feet at 2/3 of the speed of light is pretty fast. And so the error detection works better. And actually we're going to go through and you're going to see Ethernet that has 0 error detection in it because it's that reliable.
I have a question.
Sure.
Why is it multiplied by 116?
Because it's the 116 bytes that you have to take. Every frame's 116 bytes, so 2 out of 1,000 times. And really this is, yeah, that's about right. So our efficiency.
And that's just a ratio to indicate overhead versus actual data bits sent, right?
Correct. Yeah, it's a ratio to show overhead versus the amount of data bits taken.
So if you use the 175 instead, can you do that?
You can, right? But in bursty errors, it is very wasteful.
You can correct with the faulty frames anyway.
Because it's just better to detect and have them retransmit. All right, so let's get to that 16-bit checksum. So, this is actually used, and this is actually used in IP and TCP, and we're going to take a little analysis afterwards. So, let's do a checksum of 4 words. So 4 16-byte words. I'm going to use these exact numbers so that way we don't mess up the math. So we want to transmit these 16 bytes. And we want to add a checksum, right? So parity, what we do is just simply count the number of flipped ones, binary flipped ones, and then if it's even, we report 0. If it's odd, we report 1, right? But we've shown how bad that can be. So let's have something that's a little bit better. So instead of doing that, we're going to do a checksum with 16 bytes rather than just 1 bit. So that 16 bytes, we're going to append to our data frame here. Or maybe we put it in, either append it to the frame or we put it into a field or something.
16 bits or 16 bytes?
16 bits, sorry, 16 bits. So we're going to take these 16 bits, these 2 bytes, and we're going to calculate that. And how we do that, it's a checksum, right? It's actually a sum, but we're going to sum those together. And then we're going to do some other math on it at the end to make it a little bit better. So, if we sum these together, what do we get? 1, 3, 5, and 7.
16.
16, which is what?
Oh, FF.
It,
Okay.
no, 15 is
Oh,
FF.
just 16, yeah.
Yeah, so it is,
10.
it's 10,
Yeah.
right? So we're going to have a 0 down here, and we're going to have to carry the 1. And then we sum those together, what do we get? FF and 1.
31. Which is,
Well, 1 and F is
Yeah.
10 again, so
31.
it's F, right? And then we carry the 1. 1, 2, 4, and 6.
Why F is the second one? Shouldn't be 1.
No, it's F plus F, which is D, which is 1D, plus 1, which is 1F. So it's F, and then we carry the 1 again.
So 1D plus 1 isn't it?
Wait, D plus 1 would be E, right?
Yeah,
Sorry.
D plus 1 is E.
See, you did the math. And
No, yeah, you were right.
yeah, it's
Yeah.
F.
D.
It's F. Yeah.
It's F.
Yeah.
yeah.
So, yeah, F plus F is E, and then the 1. So F, sorry. I even did it in reverse, and I was like, how did I get it in reverse and still get it right? Wrong. So now we get 1, 2, 4, and 6.
Should be D.
D. And then F, F, and F. FF and F?
So FF is 1.
So FF, we already decided that was E, right?
Right.
And so another F is,
D.
D.
Plus the carry.
and then we would
Yeah.
carry the 2, right?
Right.
So there'd be a 2 up here, so this is our actual sum. Unfortunately, it's the wrong length, which often is going to be. So now what we're going to do is we're going to take this here, take it over there, and add it. So, you know, if you're doing the electrical engineering thing, right, we're not going to drop the bits off, right? We're going to carry the bits to the beginning. So now we have a D, D, F, 2. Now, this would be a good checksum, but to make it easily verifiable, we're going to do something else to it. So instead of just leaving the checksum there, we are going to take the 1's complement of the checksum. And we're going to see why we're going to do that on the verify end. Right? But what is the 1's complement of DDF2? First of all, what is 1's complement? Could be worse, could be doing 2's complement. 1's complement is simply the bit flip of the value, right? So 2, if we have 0, 0, 0, 0, and we want to make that 2, what is it?
1.
0, 0, 1, 2, 1, 0.
Yes, and so the 1's complement would be what?
Reverse.
Oh,
1, 1, 0, 1.
1, 1, 0, 1. We just bit flip it. Don't have to do 2's complement, which means that we'd have to do other things, right? So what letter is this? in hex?
13, D8.
Huh?
C.
Dot.
Yeah, it's D, yeah. So F is 1, 1, 1, 1, so what is the one's complement of it?
0.
0.
Yeah.
And conveniently,
2.
2.
So good at this.
Right, try to make things convenient. Right? So then we take that and we actually write it here. Remember, this was our sum, right? Now we're going to write 2, 2, 0, 6, D.
Hey, Professor, just to
Yeah.
clarify, when you moved the 2 over, back at the end, why did you do that?
Because we can't get rid of it. In other words, if we got rid of it, then we could actually go through a process and say, hey, let's add all of these together and see if it equals this number, right? And then assume that there was something over there. We could do that. So, but we're trying to be clever so that we can easily verify it on the end. So now let's get rid of our carry. Oh, that was actually not a carry. Now let's add them together.
I'm sorry, if we didn't have the 0 at the very end, we still can move the 2 to the end?
You don't move it, you add it.
If it
Oh,
was
we
a
add
0.
it, all right, yeah.
Huh?
Makes
If
sense.
it was 1, it would be 3.
All right,
Okay.
gotcha.
What if it was F?
Huh?
What if it was F? Do you have to carry over and change the
No,
other bits?
I don't, no,
Gosh, okay, that'll be the test, right?
yeah.
Wait. So if it is F, you don't carry over?
No, you don't carry over.
Okay.
I will verify that for sure, but I'm
Just
almost
like add it
positive.
and do it again, and if it's like, I think so, we do it again.
It's like,
Yeah.
it is, it's like, right?
Huh? All right. So, what do we have now?
Well, we have to add the new value
Sure.
at the bottom.
Yeah.
1D. 4, 9, 16. No.
So if we add them all together, what do we get? One, 3, 5, 7, which was previously 2 plus D, is what? Oh no, it was previously D plus D. This was our previous answer.
I got it.
That was previously 0.
Oh, it was previously 0. Oh,
It was
yeah.
0.
I should have wrote that down so that we could do it easy. So it was previously 0, so this is D, right?
Yes.
Yes.
Now 1, F and F is, again, F. And we carry the 1. 1, 2, 4, 6, and 2 is
E. F.
F. Carry the 1. 1, F, 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 and 2 is
No, you don't carry the 1, right? It's just F.
6, 12, 14.
oh yeah,
It's
yeah.
15,
Yeah.
so-
Yeah.
So F, F, and F plus 2. It's awful, isn't it? It's F, right? And then we have a 2 that we carried again, right? Now, we add that 2 back over the end, just like we did before. What's our answer? What's the ones complement of F?
0.
0.
We have no errors.
Oh, gotcha.
Right? And we didn't do anything tricky like, well, if the error was in one part of the byte, right? If the error was somewhere over here, then we only partly detect it. Right? Now we actually can detect any single error anywhere in the pipe.
Now we can detect any single error.
Any single error. So let's take another analysis of this checksum.
Sir,
Go
what
ahead.
type of question would come with this type of problems?
I don't think it would be a test. There might be something in the homework. This is actually implemented. So this is not like, some of the stuff we do is like we try to get you to thinking like, okay, this is why we don't do this and this is something better. This is actually implemented in IP and TCP. So let's take an analysis of something that's actually implemented and we are using today. How many errors can it detect? For sure detect. It can for sure detect one, right? Can it detect two? It possible. We have a probability now. So the probability of it detecting one is one, right? It's an absolute. The probability of detecting two is no longer absolute. Why?
If
What's the
you put
best
like
case
just
scenario?
right, and they'll still sum to 0.
Because it's a sum, right? So if one goes up and the other one goes down, then the sum still works, right? So that's always the problem with the sum is that two errors, because you can simply subtract a value if you added a value, can affect the sum, right? So, but if the errors are random, then we have a pretty good probability, right? So if our errors are random, then the is 2 to the 6. I think 1/2 to the 16th. The sum is accurate, or the inverse of 1/2 to the 16th. That the sum is accurate, right? It's very accurate for random errors. But what happens if you get bursty errors? So what is a bursty error? So when you get a burst of errors, is it like random garbage, or is it a string of ones or a string of zeros, right? So you're usually your signal is amplified or your signal is attenuated, right? So you either get a string of ones or a string of zeros. Does this checksum work with a string of ones or a string of zeros?
It doesn't detect it.
Yeah, often it won't detect it, right? So because we have 16-bit checksum and 4 16-bit pairs, right? So the length of the message isn't that long. So if we have a bursty string of ones or a string of zeros, then the checksum's fine. Because if we did this on all zeros, right, we get a checksum of 0, right? And if we did this on all ones, we get a checksum 1. Now we do have some resiliency in that we are taking the ones complement, right? So the sum of 0 is 0, but we're going to put the ones complement in there.
You would expect all F's.
Yeah. So it would now be all, yeah, it would be a string of ones, right? But you can see if you get bursty errors of zeros and then ones and then zeros because something's going wrong with the line, things might go through that are correct. But now you understand why we're doing the ones complement. All right. As awful as that one was, let's take a look at CRC. Who are my guys that have taken cryptography already? All right. Remember finite fields? No, I forgot it with lots of beer.
I was depending on that.
Huh?
You didn't get the finite fields in cryptography language.
Yeah. I blame that other professor.
So what we want to do is let's take a look at something very, very small, and then we'll actually take a look at something that's actually in reality, right? So to take an idea of what a CRC actually does, let's say that we are going to have a number, and that number is 302. And then we want to have k check bits. In this case, we're doing easy math, so we're going to do 1. And then we want the cyclic check, which we'll see in a minute. This is really a modulo number, and we're going to set this one at 3. So the idea is we have a number that is 302, and we want to append something at the end so that the checksum is evenly divisible by usually a very large prime, right? So we're going to use a very small prime, and we're going to have that modulo 3. Modulo really, everybody understand what modulo is, right? It's just do a division and throw away the quotient, keep the remainder, right? So 302 modulo 3 is what?
2.
Is 2. This is why we pick 3s. Everybody remember the trick in grade school where you simply just got to add these together, right? Did you know that? So if you had like a number, you want to know if it's evenly divisible by 3, you just add those together, and if it's divisible by 3, then it is. That's why you pick easy numbers, right? So 302 is not evenly divisible by 3 because 3 plus 2 plus 0 is not, right? You get a modulo of 2. So what do we need to add to this to make it evenly divisible? 1. This is the basis of CRC, the easy version. Of course, our modulo is going to be much bigger, and our input is going to be much bigger. And we're going to do this over a finite field because there happens to be properties of finite fields that make it very easy for the computer to do the math.
So what C is for?
C was the divisor, so it's the prime number we're dividing by.
And, okay, so we didn't use the 1 digits, the K.
Yeah, we did.
Yeah, we did.
Yeah, we did.
3021, he
Three.
appended it to the end.
Yeah, it was right here.
Oh,
This
okay.
is K.
Good.
This is our 1-digit CRC, right?
Thanks.
So now let's do CRC for real. Actually for real. So let's take the finite field of x to the 7th plus x to the 4th plus x to the 3rd plus x to the 1st. Right? And what's the binary representation of that? 0, 1, 0, 1, 1, 0, 0, 1. Right?
What were you looking at when you were doing that?
Yeah, boy.
Oh.
So this is plus nothing, right? So this is 0, 1, and then there's nothing there. 1, 1, nothing, nothing, 1.
Gotcha.
Right, it's a finite field over modulo 2. So if the if the x doesn't exist, then that's 0. Okay. And so this is going to be our generator. And we want to,
Question, why do you have two zeros?
Oh, s-
Four,
Right
five,
here?
6, 7.
because this is,
X first.
Three power 6.
this is 1x to the 7th plus 0x to the 6th plus 0x to the 5th plus 1x to the 4th, right? But normally in math, you don't write the zeros because they're irrelevant. It's multiplied by 0. Okay. Now, let's see. So this is the actual generator for CRC. So we could do that, but I got an easier example. Let's do a much smaller one, but it'll give you the idea, and you'll see why we're going to do a smaller one. Let's take, instead of having that generator, let's take a generator of 1011. There's 2 zeros. And we want to take the data, so now our generator is x to the 4th plus x to the 1st plus 1, right? Yep. And then our k bits, we're going to have 4 k bits instead of 32. And we are going to send the message 110101111. So we do the exact same thing we did with easy math, right? We are going to divide by this generator. We're going to have 4 check bits, and this is the message that we're going to send, and we want it to equal 0, right? So our message becomes 1 1 0 1 0 1 1 1 1 1, and then we extend it 4 bits because of this. Our generator is 10011 because this is our finite field, and we divide into that. Now, it's long division and it's terrible, but it's not as terrible as the other long division because we're over modulo 2. So there are some tricks that we can do.
All right, so we messed up the division a little bit, got off track, so I thought maybe I'd put it on line paper this time and see if we can get this a little more correct for the record. So in class I said that our generator was x to the 4th plus x to the 1st plus 1. The binary representation of that, let's go ahead and work it backwards. That's x to the 0 is true, x to the 1st is true, x to the 2nd is not true, x to the 3rd is not true, and x to the 4th is true. So this is our binary representation. And our k bits is going to equal 4. And let's go ahead and write what let's write our generator here. So 1 0 0 1 1. And we're going to divide that into our bit string that we're going to do our CRC for. So that's 1 1 0 1 0 1 1 1 1 and 5 ones, and then our k bits right here. So let's go ahead and start the division. That is 1 0 0 1 1, and we do our subtraction modulo 2, which is XOR, right? So it's 1 0 0 1, and then let's bring down this one right here, and do it again. 1 0 0 1 1. Well, that was very convenient, right? So obviously this is all zeros. So let's bring down 1 1 1 1. Now we're going to put 5. And notice we're not keeping track up here because we're going to throw that away because all we want is the remainder. So we're going to bring this blank down, and blanks we're going to represent a 0. So 1 0 0 1 1, right? So that is a 1, that is a 0 1 1, and then we bring down another 0 right there, comes from up there, and so that is 1 0 0 1 1, and so we do that one, and that is 1 0 0 1, and then we bring down this one, right? 1 0 0 1 1, and we're running out of room here. So you notice that this is going to end up. We could squeeze a line down here at the bottom of our page. Right here. So these are all zeros, right? And then we have a 1 here, and this is a 0. I'm gonna keep track of that because these are our K bits. So 0 0 1, right? And then we bring down the 0. So this right here, our K bits, 0 0 1 0. If we wanted to evenly divide it up there, we do 0 0 1 0, and it would evenly divide, right? And so this becomes our cyclic redundancy check.
Yes, that's correct.
That is correct. He actually did it all out, right? The remainder is 10. Now, just like before, and this is not where. I don't think this is going to be on the test because everybody would just screw up in dyslexia things like I just did. So we'll forgo that on the test, right? But just like before, right? All we want is it to modulo out to 0, right? So we just add 0 0 1 0, and this modulates. It divides evenly. That's all we need.
Okay. I'm lost in the second after we have the second 0. So beyond that, we have 1 0 0 0 1, but it should be 1 0 0 1 1, right?
Yeah, right under the
That's
2.
right.
No,
No,
number
no.
2.
The line you changed
Okay.
originally.
Yep.
No,
So
next
below
line down.
this one,
Next
it should
line.
be 1 0
Okay.
0 1 1,
There
right?
it is. Yeah.
Right.
Yeah.
So
But it's still,
okay,
It divides out to 10.
yes.
then 1.
Gotcha. Anyway, solve it through.
Because this goes.
Because that
10.
becomes a 0,
Yeah.
right? And then
That's
you
the
have 0,
remainder.
1 1 below that, and you get,
Yeah.
then you bring down the 4th 0, and it makes it 10.
This is exactly how CRC is done. What are the advantages of this?
Making sure that has not been changed or no errors.
Yes. So this is not a sum, right? Because we're modulating over a prime number, right? In order to get the same modulo, what do we have to do? Right. So in a sum, if we add 1, we need to subtract 1, right? In a cyclic redundancy check, if we add 1, simply subtracting 1 isn't going to make a difference, right? We actually have to make it factor or divide cleanly into this large prime number, right? Large-ish, right? So our generator for this is x to the 7th, so it's 8 bits, right? But that means that a random error, in order to get that thing to work out, we actually have to have 8 bits of error. So now you start compounding probabilities of, hey, if I got this error here, then I need this other very complex error over here for it to make sense, right? So a COC is it's not cryptographically strong, but for random errors, And it's not cryptographically strong because we can simply do a string of things the same way that this works and make it the CRC the same, right? But that takes actual knowledge of the algorithm, and just throwing random errors at it isn't going to make it great. I will put this in a very neat tabular thing on the video because this is awful. But you can see now that it's very simple for a computer to calculate because it's just a string of XORs. XORs are a single clock in most machines. So it's, in this case, we'd have to do probably, if it was 4 bits like the last one, then we'd have to do 12 XORs, right, to get the correct answer, which is fast on computers that have billions of clock cycles per second. And in 32 bits, it's not that big a deal. And so now your errors, the probability of having 2 errors becomes 1 over 2 to the 32nd, and that are correct in the right exact spots. And 1 over the 2 to the 32nd is a big number, right? Well, it's a very small number, so it becomes a very difficult probability to overcome. Right? It's 1 over a billion. And while it's not very fun for us to calculate in class, the computer can do it very easily. So now, so we talked about error detection, we talked about error correction. But we've always said, hey, if we detect an error, then we retransmit, right? That's actually not as simple as it seems. Because the question becomes, how do you, in a 2 receiving system where one person is not communicating well, how do they know when to retransmit? So we do a timeline diagram. You remember this from setting up sockets, right? Where time is going down. The very simple way is to transmit. And this is the receive. This is send. Right? And then do an acknowledgement. Then do a transmit. And then do an acknowledgement. What are our scenarios here for retransmission? So something went wrong.
No acknowledgement?
Not.
So let's say
the transmit after that one.
Huh? Yeah. So we do a transmit and we do acknowledge after we receive it. But let's say that the transmission was an error, like we've been talking about with all these error detection schemes, right? So then what we do is we don't do anything. So it could be an error, and if it's an error, we don't do anything. That actually serves 2 purposes, because it may have been transmitted, it'll also lost. So that way, the transmitter, regardless of whether it was an error or whether it was lost, we don't care. And then we put in a timeout. And then after a timeout, if we didn't receive the ACK, we transmit again. And then we get the ACK. So this works for error or nothing received. What's our other error condition? What if we transmit and the ACK isn't received?
The receiver will start the timers and
Yeah, right? Then we can transmit again after the timeout. Now we've introduced another problem. How does this guy over here know that this packet is a duplicate of that packet?
the acknowledgement is cumulative, so the centers will be able to know whether this one is duplicate or not.
So from this guy's perspective though, he got a transmit, he received an ACK like he was supposed to,
Okay.
but the ACK was killed. Either it was an error or it was dropped or something in the network, right? So from this guy's perspective, the guy, he didn't get the packet, so I'm sending it again. And so from this one, he thinks this is frame 1, right, and this is frame 2.
Nice number.
Just, yeah, the sender numbers the packets.
We can number the packets, right?
Puts them in order.
So it turns out if we're doing this, just very simple, we only need to number the packets 0 and 1.
Oh, yeah.
Huh.
Right? So we send transmit 0, we get an ACK 0, and then transmit 1. Right? ACK 0 doesn't go through, then we get a transmit 0 again. And then he will know that this is a duplicate packet. This only works for this type of scenario. This is called a stop and wait scenario. Right? Which means I transmit and I don't transmit again unless the timeout fails or I don't get an ACK.
Shouldn't the receiver start the timer?
We agree on the timer beforehand.
Okay.
So, but the receiver doesn't send anything ever unless it's an acknowledgement. So if here he would send an ACK 0. So that means that the sender knows to flip the bit. The ACKs are always in line with what he received. So this guy doesn't increment bits. This guy increments bits. The problem with this is that it's stop and wait, right? So if we have a network that's stop and wait like this, and we have a 50 millisecond time, and let's say that our timeout is right at 50 milliseconds too. That way it makes the numbers easy. What is our time to transmit a frame? It's 100 milliseconds, right? It's 2 times the transmit time, right? Because D is equal to, transmit time is equal to 50 milliseconds. So now let's say you're going to send a actual, real frame, and in a commercial network, the frames are like 64K. Right? If we have a 64K transmit time and we have 100 milliseconds, right, our bandwidth's not going to be very high. It's going to be really, really low, actually. And making the line fatter is not making it any better, because we have to wait for an acknowledgement before we send again. So how do we fix that? We want to take big pipes, right? We want to cram the pipe always in networking. We want to cram the pipe as full as we can get it. So how do we do that?
Transmit a bunch and then have him acknowledge the
We
numbers.
transmit a bunch.
Back saying these are the ones that I got, and if there's any zeros, I retransmit those.
Correct. So what we do is we transmit a bunch. let's say like that is the right, that's the same time, right? We make our counter bigger. And then our counter only needs to be as big as our transmit time. And now we can fill the pipe up with as many as we want. And we still get all the benefits that we had with the stop and wait, with the exception of the tiny bit of overhead, because we've made, instead of a 1 bit, right, we're probably doing a byte. And this is actually, this actual thing is called ARQ.
So instead of the acknowledges being like separate lines, it would actually just be like A0 through A4 all on one line, head and back, right? To save space, so that you're acknowledging fewer times than you're transmitting.
Maybe, and maybe in a higher level, but at the like the link layer, which we were talking about, you just send an ACK for every receive you get, just back and forth. The ACKs are very small, and so they don't actually take up a lot of bandwidth. We will have some interesting things when we're doing wireless, which we will not get to today, unfortunately. But where you receivers and senders can't hear and talk at the same time. Right, so just to kind of give an idea, since that's the topic, on a wire, you can listen and talk at the same time. Why?
Two different frequencies.
You can do 2 different frequencies, right? But you can also listen and talk on the same frequency. Because sometimes it's 2 different frequencies, sometimes it's 2 different wires. But in a very simple scheme where it's just one wire, the deal is you're not talking very loudly. And there's very little attenuation on a wire. So wireless is completely different. So the attenuation on the wire is literally the resistance of the wire, right? In wireless, it has nothing to do with that at all, right? If you send out a signal, right? It attenuates at R squared. It's the law of squares, right? So if your signal strength here is X, right, at 1 meter, at 2 meters it's what? It's 1/4 X. At 3 meters? Huh?
1/3.
It's 1/9. Because you're actually doing the radius of a circle,
Yeah, one of ours.
or the radius of a sphere, and that is attenuating at R squared, the radius squared.
Is that for all wireless?
For all wireless.
Yeah.
There aren't certain.
So you can have directional antennas, right, that will attempt to focus the beam in a certain direction and get better, but in something that broadcasts, a broadcast medium, whether that be the light bulbs in this room or the Wi-Fi in your computer, right? Every time the radius increases, it's the square, a fraction of that square. It's called the law of squares. Why can't you build a metal detector that detects gold, right? And build a really gigantic one. They have metal detectors that detect gold. So why don't we have a really gigantic metal detector, right, that detects gold in a square mile? And the deal is because you would irradiate yourself, you would fry yourself, right? With the amount of energy it took to do that, right? Because the amount of energy is decreasing at an exponential rate as further it gets away. So in wireless, when you're talking, what you are saying is no kidding, like 1,000,000 times louder than what you are hearing. 1,000,000 times. So while you're talking, you can't hear because the signal is 1,000,000 times. So if our signal is, the width of the board, right? It's way smaller than that dot I just put on there, right? Which is way smaller than the noise that's in the signal. So it's very difficult to hear. But on a wire, it's not the same thing because the energy is directed. So the signal propagates down the wire, right? And in copper wire, the attenuation isn't all that great. It's not that large, and in fiber, it's almost non-existent. So that way, what you're broadcasting across that wire is relative to what you're hearing there's not that big a delta. So you can listen at the same time as you talk. Just like we were talking in this room, right? If I had a bullhorn and I was lecturing to you guys on the other side, right, and you guys could just barely hear me, if somebody was talking in the crowd, you wouldn't be able to hear anything I said. And if you were talking, you wouldn't be able to hear anything I said. Possibly not that I even said anything at all. Right? It's not that you can't just decipher, you can't actually tell that somebody talked. I think we got just enough time to do multi-class. Yeah, there's no way. I'm not gonna do it. Yep. We'll save it for next time, or on Wednesday.
So do we know what our next homework's gonna be, or?
So I was hoping to get far enough down to do questions. We're not even gonna get to questions on Wednesday. So I will put out so it was suggested to me that we put out the questions that we're gonna do in class beforehand, so you can kind of get an idea, and then we'll work through them beforehand. At the same time, I will put out those questions, and then I will put out the homework questions, just like I did the last time, where they become live at the end of class.